Alright, this is a video for mechanical waves for Regents Physics. I'm only covering mechanical waves. I'm not going to be discussing electromagnetic waves in this video. Also, I'm just going to be running through concept here. I'm going to show you a little bit of diagramming with the waves themselves, but I'm not going to expand into too much depth. This is a review video after all. Okay, wave types. Before I start talking about the different kinds of waves, let's define what a pulse is. A pulse is just a single vibration. So it's like, I like to think of it as if I'm holding a taut rope, maybe one end is tied down on one end and I'm holding the other end. If I just shake my hand up and down, a pulse is the single hump that goes down that wave, not that wave, down that rope. Okay? If I were to continue to shake my hand up and down, that would be considered a continuous wave or a periodic wave. That would create an actual wave that travels down the rope in a very repetitive fashion. It's periodic. It repeats itself over and over again. There are, of course, non-continuous waves or non-periodic waves. When we deal with Regents level physics, we're really just talking about either a pulse or a periodic wave. So we have two main types of mechanical waves we'll look at. We have the transverse wave or longitudinal wave. Your transverse wave are the ones that look like typical waves. If I were to ask students before they take physics to draw a wave, a lot of students will draw something that looks like what I've been drawing already. It's an up and down wave. Transverse wave, another way of defining it, is the medium itself, the particle, the rope, the water, whatever the energy is traveling through, will oscillate perpendicular to the direction of the wave itself. So if the wave is traveling left to right, the rope or the water, whatever, will move up and down, which allows me to bring up a different concept about all waves. I should have led off with this. All waves are simply energy. A wave is energy, and for mechanical waves, it's energy traveling through a medium. So the rope itself isn't the wave, it's the energy traveling through the rope that's the wave. A longitudinal wave is more or less a compression wave. It's one in which the energy and the motion of the object travels along the axis of the energy itself. It's hard to draw a longitudinal wave. Think of a slinky that's going to be compressed in some zones and expands in other zones, and then compresses again, and then expands, and then compresses again, and then expands. It's really hard to draw these, but we're going to get a vibration back and forth as the energy travels down the medium itself. Sound is another great example of a longitudinal wave. If I were to try to draw the air particles themselves, in a sound wave we'll have an area where it's really compressed, and then you have more of an area where it spreads out. So I'm trying to get thinner apart, and then it starts to compress again. Again, it's very difficult to draw the longitudinal waves. You won't have to draw one. Interference is a phenomenon that occurs when energy itself is passing through more energy. So when we have two waves acting in the same spot, what do? We have constructive interference and destructive interference. Constructive interference is when the two amplitudes or the two crests or the two troughs of each wave are on top of each other. Or destructive interference is when we have one wave's crest is on top of another wave's trough. I'm going to draw these two out because it's a lot easier to show. So if I have one wave that's like so, and it's traveling to the right, I probably shouldn't have had it slanting up at an angle like that, so let me try to rotate this a little bit. If I have one wave that travels to the right, if I take another wave, maybe it's completely different, and I take it such that the peaks are on top of each other. So this red peak is on top of this blue peak, and this blue peak trough is on top of this red trough. We're going to find construction takes place. If I were to create an equilibrium line here, I might call this a +1, and this guy to say +3. Well, they will create, therefore, an overall wave that adds together of +4. So we have an amplitude of +4 here, and then we'll have -1, and this meant to be -3. I got kind of lazy. So they will add together as well in the negative sense to -4. This is construction because the peaks add together. They don't cancel each other out. So if you were a dude standing on the blue wave, you might get thrown up a little bit. Standing on the red wave, you might get thrown up a little bit more. But if you were standing on that blue wave, you get thrown up a lot. Destruction, really more or less, is a similar idea, but instead of positives being on top of each other, we have a positive on top of a negative. So I'll slide it over here. Destructive interference takes place when, again, we have one part of the wave is canceling another part of the wave out. So if I were to assign algebraic values here, this might be +3 again, and this is -1. So it'll create an overall wave of +2. Since there was no blue wave over here, the only spot of interference is where the two waves are actually on top of each other. A standing wave is something that comes from interference, but it's more specific. It's actually very specific. Definition of a standing wave, you absolutely need to know. A standing wave is a wave that has is when two waves of the same amplitude and frequency are passing through each other, traveling in opposite directions. You most often get this when you have a wave reflecting off of a source and coming back. So take a string, for example. Maybe you send an energy, a periodic wave, down that string. That periodic wave will travel until it gets to the end of the string. It'll then hit a point and it'll reflect and it'll come back. But it'll come back such that it reflects on the opposite side in which it was being transmitted. I'm going to try to draw this for you, but it's not very easy to draw. Highly encourage you to check out standing wave simulators or watch videos on YouTube. I'm going to flip this so it did reverse, like I said, and I'm going to change its color just so it pops out a little bit. And so when we have these two waves approaching each other in opposite directions, but they have the same frequency and the same amplitude, which I tried to do, but I got a little lazy. When they're on top of each other, two things start to happen. In the very beginning, where it looks like we're going to get constructive interference, these two peaks are in the same direction. But then as they continue to move, you'll all of a sudden get destructive interference. And they continue to move, and then you'll get constructive interference again. And you do this over and over again fast enough, you get what we see as a standing wave. It's a wave that appears to be standing still. It appears to exist in two spots. I'm going to draw a standing wave now. We have, like I said, a wave that appears to exist in two spots. I'm going to draw two full wavelengths just so I can try to articulate a few more thoughts that deal with standing waves. So it went down and then it came back, and we're ultimately going to get a level of constructive and destructive interference. This typically happens so fast that if you're actually looking at it, it looks like this weird two-wave on top of each other thing. It's not actually existing in two spots at the same time. It'll be going back and forth. And when I teach it to my students, I say, take your hand and wave it in front of your face over and over again really fast. It almost appears like your hand is taking up more than one spot. It almost looks like your hand is everywhere that you're waving it. This is kind of true for standing wave. The reason why I drew it out like this is I need to point out a few more things on the standing wave known as nodes and antinodes. The points where we see no motion at all, where the medium never appears to move, these spots here, they appear to stay on the equilibrium line, which is often referred to as the nodal line. These are your nodes. Nodes, no energy is detected. If I had an energy meter here, it would notice nothing. The spots where we're getting maximum amplitudes, okay, anywhere from crest to a trough over and over again, these guys are my antinodes. But this is one antinode, it's not two. So in this overall standing wave, I have 1, 2, 3, 4 antinodes, and I have 1, 2, 3, 4, 5 nodes. Visually, it should be pretty easy. I hope you check out some other videos though, because conceptually it's not as easy as I made it sound. Wave properties. I probably could have let off with this because it's dealing with the attributes of the waves in which I've already been discussing, but I digress. I moved along. Wavelength is the distance a wave travels in one complete cycle. So I'm going to quickly draw a wave over here so I can point some of these things out. So here I have a wave. This would be my equilibrium line. My wavelength is where the wave repeats itself. So maybe it's from crest to crest. This would be one whole wavelength, written as lambda. Or it could be from this point to this point. It's the same length. It's also one wavelength because that wave is back again. It's where it repeated itself. Lambda is the Greek symbol that we use for wavelength. And it's length, so it's measured in meters. Amplitude is the distance the peak is away from the equilibrium. So it'd either be the crest to the equilibrium or the trough to an equilibrium. For a periodic wave, they're the same. So if this whole thing measured to be, let's say I had a meter line here, if this whole thing measured to be 2 meters, this distance here is 1 meter. Which means this is also 1 meter. Your frequency and period kind of go together, but they're not the same thing. Frequency is the number of cycles that pass a given point per unit time. Period is the amount of time for one cycle. So by that definition, they're actually inverse of each other. If I know one, I know the other. If one is large, the other is small. That's simple. If you complete a lap around the track in 60 seconds, your period is 60 seconds. That's the time for one wave, one cycle. Your frequency is well under that, though. That would be the number of laps you complete in 1 second. That's going to be 1/60th, because you only completed 1/60th of the lap in 1 second. 60 seconds later is when you completed a whole lap. That was definitely not 60 ticks for those that were counting. Your speed of the wave is actually the same as your standard average velocity of anything. I don't need to erase my whole wave. Let me just erase this stuff. Velocity is distance over time. In terms of a wave, though, we're going to use wavelength over time. The time for a wave is the period. And since period is inverse to frequency, we often write it as lambda f, or f lambda. In your reference tables, it has it written in as lambda f, or f lambda. Because its speed, it is measured in meters per second. The speed and wavelength depends on the medium through which the wave is traveling. So as a wave enters a more dense medium, it will slow down. If it enters a lower dense medium, it'll speed up. Let me get back to frequency. I meant to point this out. Once a wave has been created, okay, so long as you're not changing anything, once the wave has been created, it's already propagating outward, its frequency and period will never change. Definitely know that. It's extremely important. In fact, I do have this down here. I probably should move it up in my notes. It does not change once it's been created. So if it enters air or water or a more dense rope or whatever, the frequency or period, they will not change. Instead, what will change will be the speed. And if frequency can't change, the wavelength also must change. Doppler effect. It's this apparent change in frequency. Because like I said before, does the frequency actually change? No, it does not. It's the apparent change in frequency. Doppler effect is often heard when we have an ambulance or a police car rushing past us, or we're listening to a train drive by, and it sounds like when the object is getting closer to you, it sounds like it's getting higher and higher and higher pitch, and then after it goes past you, it drops in pitch, so you get that excuse me, you get that kind of sound. Don't mix it up with loudness. Don't get me wrong, loudness will change. As the source of sound comes towards you, it will sound louder. But I'm talking about the actual pitch. It'll go from a high pitch to a low pitch, or a low pitch to a high pitch. It will literally sound like a different note. I can show this by taking an object and representing a wave that's propagating outward in 2 dimensions away from it. Okay, so a wave is leaving left or right. Maybe there's a person just yelling and screaming. Now let's make it a monotone, a single frequency. So maybe we have a speaker here playing a C, and that is shooting outward. As long as that person and that speaker and the person listening to it isn't changing their location, it's going to always sound like a C. But if either the person or the source move towards or away from each other, the wave lines will begin to crowd up and appear to be a different frequency. It's going to be difficult to show this on here. Just as with these standing waves, I do encourage you to check out some simulations if this is confusing you. But let me show you one example. Let's say I have the source is moving to the right, so it's traveling to the right. As it travels to the right, the sound waves in front of it will bundle up, and the sound waves behind it will be further apart because it created a sound wave and it's getting further away from it. So if you were a person standing here listening to it, it would sound higher in pitch than it should be up in this earlier example. And if you were over here listening to it, it would sound lower in pitch because they're further apart from each other. Again, it's the apparent change in frequency. Bottom line, what you need to know is if the relative distance is decreasing, or another way of thinking about it is if the source and the observer are moving towards each other, the frequency pitch goes higher, and if they're moving away from each other or the distance between them is increasing, the pitch gets lower. Pitch and frequency are interchangeable words for sound. Color and frequency are interchangeable for light. So we get this phenomenon in light as well. Although I'm not really focusing on light in this video, understand that Doppler effect is there. You're going to get this red shift versus blue shift. Red means that we're getting a lower pitch or lower frequency, I should say. Blue means we're detecting a higher frequency. Again, though, the frequency isn't really different. It's just what is appearing to be different, observing to be different. And the last two concepts, resonance and diffraction. Resonance is such a gnarly, awesome concept. Anyone that goes through a full year of physics, I'm sure, will love the idea of resonance. All kinds of cool stuff out there. I highly encourage you to type this into YouTube. You'll see some pretty fancy videos. Resonance is when it's like when an object itself is forced to vibrate as a result of an outside vibration. So every object has at least one natural frequency in which it wants to vibrate at. You can actually detect it by knocking on it, tapping it. That signature sound you hear is its natural frequency. If we have an outside source matching that frequency, maybe it's a speaker playing the exact same frequency, it will actually cause this object to rattle from a distance of afar. Anyone that's in music, like say band, will probably notice resonance taking place all the time when the music stops. Sometimes they'll hear some other instruments continuing to vibrate. Other examples given here is when an opera singer can smash a glass with their voice, or you can get a wine glass to vibrate with your fingers. Musical instruments all incorporate the concept of resonance. There's so much here. It's pretty awesome stuff. Know the definition, understand that, quite frankly, in order for resonance to occur, the outside frequency must match the natural frequency. If the frequency changes, resonance does not take place. Last one I want to talk about is diffraction. It's the apparent bending or the actual bending of the wave around through a barrier or an opening. So think of water going through an opening. If I have water, nice even waves approaching this opening, that water will all of a sudden ripple away. Take a rock, drop it in a pond. That rippling away is another example of diffraction. Understand that as the opening decreases, the amount of bending will increase until that opening, if it's smaller than the wave itself, it won't happen. The wave will just bounce off. So you can't get infinitely small, but in this example, you might get some bending. I'm trying to show bending, but it's not the best. Here we're going to get a little bit more bending, and here it's going to be really nice, tight diffraction bending. All right, that's your basics for all of wave mechanics. I think it's a solid review, but of course it is indeed only a review. I encourage you to brush up on anything else you need to brush up on. Thank you.